Okay. So when we move from the green schist species to the amphibolite, so what are the, sorry, so these are the summary of the changes. Okay. So the plagioclase moves from anorthite, low anorthite content to anorthite 15 to 18. This is what we call as the peristeroid jump. The amphibole, there is an increase in the Al2-3 content of the amphibole. That is also pretty significant. Okay. So the chloride becomes more magnesium rich and finally disappears. Okay. So the moving into the amphibolite species is marked by the disappearance of chloride. So within the green schist, the chloride becomes more and more magnesium rich that we discussed, and then it finally disappears to form amphibole. Okay. And then obviously there is a decrease in the epidote content, and epidote, some amount of epidote still remains in the amphibolite species. We will discuss that right away. And but the content obviously decreases quite a lot. Okay. So if we look at the common reactions which occur from the green schist to the amphibolite species, you will see that, okay, you don't have to remember exactly the reactions, but what you see is that all the reactions have a similar trend where the tremolite, okay, or actinolite, which is the aluminum-free amphibole, okay, reacts with albite or chloride epidote. So all the aluminum bearing phases to form hornblende or varieties of hornblende which has aluminum. Okay, so these are obviously end member reactions, but what we have is a solid solution reaction, and we have what we get is hornblende. Okay, so if you look at this reaction, there is tremolite, which is the aluminum free, plus albite, which is sodium aluminum, and what we get is edenite, where sodium and aluminum gets into the hornblende. Okay, and quartz is generated. If you look at the other reaction here also, there is tremolite, okay, which is aluminum free, reacts with chloride, epidote quartz to finally form schermakite. Schermakite is also, we discussed yesterday, is an aluminum bearing amphibole or hornblende. Okay, so what you see is that all these reactions lead to the formation of hornblende, which is the major mineral of the amphibolite species, and this is where the name of the species also comes from, or name of the rock also comes from, right? So rich in amphibole, and therefore it is amphibolite. So this is where the name of the rock comes from, right? So the breakdown of the chloride generally marks the end of the green schist species. Okay, when do we know we are out of the green schist species? Is the breakdown of the chloride. So chloride is the mineral or the characteristic mineral of the green schist species. It never, or it does not cross into the amphibolite species. Okay, chloride completely breaks down and forms hornblende. Hornblende is a mineral of the amphibolite species, and it is the most characteristic mineral of the amphibolite species. Now, epidote is another mineral which is most common in green schist species. Its amount decreases in the amphibolite species, but in certain conditions, there can be some epidote which are left in the amphibolite species conditions, which we will see now at what conditions. Okay, so yeah, here are some pictures of the rocks in the amphibolite from the green schist to the amphibolite species condition. For example, these minerals, this is epidote, how it looks like. Okay, and slowly this is more of the green schist species where there is a lot of chloride and epidote. Okay, and we will see that what happens just in the next picture, that how it looks in the pure amphibolite species. So this is the transition. This is how the rock looks like when it is getting or when there is a transition from the green schist to the amphibolite species condition. Okay. Right. So there is another term that you will you will commonly come across is actually the epidote amphibolite species. Okay. This is not in the species diagram because such a nomenclature or this is a special nomenclature And what do we actually mean by epidote amphibolite fascies is that within the amphibolite fascies condition where epidote is also stable. Okay, so epidote is stable. Why it is important? Because it marks a certain important reaction, and this is only a special condition, a special pressure temperature region where epidote and amphibole or epidote can be stable or can remain in the rock within the amphibolite fascies condition. Okay, it is also not throughout the amphibolite fascies, and this nomenclature of this species does not exist for any other rock type. It is only specially for the mafic rocks. Okay, especially for the mafic rocks that this nomenclature is sometimes found in the or very frequently found in the nomenclature. Sorry, in the literature, and I wanted to just describe that what it actually means and when does this happen. Okay, so what is exactly this epidote amphibolite fascies? Okay, so let us try to understand this diagram, right? So this is basically, this is the region what we are talking about in the fascies diagram, and let us try to understand this diagram. Okay, so this is the temperature and this is the pressure. The exact values are not given, so it's practically in this region which is shaded out here, and you can find out at what temperature. Okay, so this temperature sensitive line, okay, this is the chloride out reaction line. What do you mean by that? Is that on the left side of this reaction line, chloride is stable. Okay, and if you move across this line, chloride not stable. Okay, so it reacts to form hornblende. Okay, so therefore on the left side you have actinolite. Okay, the amphibole without aluminium, it reacts with chloride. We have seen the shown the reaction. And on the right side it is hornblende, right? So practically this line, as we said, chloride, the end of chloride marks the end of the green schist species. So practically this line marks the end of the green schist species. So here it is green schist. On this side, it is amphibolite species. Okay, so practically this line marks the entry in from green schist to amphibolite. And this boundary, what you see out here, practically follows the chloride stability field. Okay, from green schist to amphibolite. So the boundary at 500 degrees centigrade practically is along the chloride stability field, where the chloride goes into breaks down to form hornblende, or reacts with actinolite to form hornblende. Okay. On the other hand, you see another reaction line, this black one, which is about the epidote. Okay, so what we have is that, so albite and epidote, epidote being a denser mineral than plagioclase. Okay, epidote is a denser mineral than plagioclase, so it is stable at higher pressure. Okay, relatively higher pressure. So we know that anything in earth sciences or in mineralogy as well, the minerals which are more denser, okay, are always favored at higher pressure because they can sustain the pressure, or they can withstand the pressure much better. Okay, the natural reaction of a mineral under higher pressure is increasing its density, changing its structure by and increasing its density. Okay, so it's a more compact mineral which are more stable under pressure. Okay, so it's a general rule that any mineral which is relatively more denser, sorry, which is more denser, is always favored at the higher pressure. Now within this reaction where the calcium rich plagioclase or albite plus epidote goes to calcium rich plagioclase, epidote is relatively denser, so it is relatively favored at a higher pressure than the calcium bearing plagioclase, and therefore the reaction line is kind of shallow. Okay, and these two reaction lines meet at a pressure which is around 3.3 kilobar. So above 3.3 kilobar, what you see is that, right, within this region, what you see is that you go into the amphibolite species where you form hornblende, but epidote is still present because you have not crossed this reaction line. Okay. If the temperature, let's say the PT condition, your geothermal gradient moves in this along this path. So what you will see is that first the chloride is gone, chloride is unstable, it has formed hornblende, but within this region, epidote is still present because it has not crossed this reaction line. Only when it crosses this, then the epidote breaks down to form calcium-rich plagioclase. Okay, and so the intersection of these two reaction lines actually forms a zone. Okay, actually forms a zone where within the amphibolite species means with the stability of hornblende, no chloride, epidote is also present, and this is what we call as the epidote amphibolite species. Okay, this has a special significance because why do we have there is a special significance in the mafic rock? Because if epidote and hornblende are present together, we can directly say that the pressure is above 3.3 kilobar. Okay, and we are within the amphibolite species condition. So the temperature is above 500 degrees centigrade and the pressure is above 3.3 kilobar. So we can directly have understanding about the pressure and the temperature condition of metamorphism. Okay, so that is the special significance, and many authors have denoted this special region or this zone as the epidote amphibolite species. Okay, and this is roughly the region where these two are stable together. Right. In this range, we do not see that. Even if we cross along this, so if we cross this boundary, then epidote is completely gone, and we are left with only plagioclase and hornblende. Obviously, hornblende and plagioclase is definitely there, but along with that, if there is epidote, we call it as the epidote amphibolite species. Okay, any questions on this?
Sir, the line in the in the left part that chloride out and on the right part which you circle the red one. These are the both the same or some differences?
Sorry?
Like, so the left part, like the left part diagram is just the zoom out of the right part
Yes,
diagram.
yes, yes,
Or
yes, yes. It's basically the same thing on the same thing. It is showing the only that part. Okay,
yes,
so it's why the same diagram you can see it's all both are pressure temperature axis. On the x-axis you have the temperature, y-axis you have the pressure. So if you cut out only this part, okay, and put it here, so this is how it would look.
yes, sir.
Right. So where this line and this line, this is how it would look. Okay. Any other questions?
Sir,
Yeah.
in the left diagram, the only the black bar shows the field of epidote amphibolite, or also the zone above the black bar.
No, no. The black bar is the reaction line. The epidote amphibolite species is the shaded area,
Yes,
right?
sir.
So this part, this gray shaded area is the epidote amphibolite species,
Oh,
above which epidote is, yeah, above which epidote, okay, above which epidote is stable within the amphibolite species condition. This entire region. So this is the same as this shaded region.
okay, sir. Okay, sir.
Okay. So this is the region. This is the shaded region is actually the epidote amphibolite species.
Okay, sir.
Okay.
Yes, sir. Okay, sir.
Okay. Any other questions? Okay. So after I finish this, I'll ask questions to you. Let's see how much you have studied and read. Okay. So the typical assemblage for the amphibolite species is obviously what you can see is hornblende and plagioclase. Okay. So all the minerals, so the mineralogy is very restricted. So hornblende and plagioclase is a typical mineral of the amphibolite species. And along with that, at sometimes you can get epidote, as we just saw. Garnet clinopyroxene quartz we can all get, but as you can see, these are plus minus, which means that they may or may not be there. But hornblende and plagioclase will always be there. Any mafic rock metamorphosed within the amphibolite species condition will always contain hornblende and plagioclase. The other minerals may or may not be there depending on certain conditions, but hornblende and plagioclase is the must. Okay. Now you can, we have done the ACF diagram, right? We have done the, okay, is it my voice is breaking?
Yes, sir.
Can't really, maybe it's the internet issue.
Yes, sir. Only for some seconds, sir. 10 seconds.
Okay. Okay. So if I have to repeat, then tell me. So you have done the, ACF diagram, right? So what you see is that plagioclase plots out here. Here is hornblende, here is garnet. Okay. This shaded region is the average composition of the mafic rock, right? So what you see is that we can draw tie lines between the minerals which are stable together. Okay. So we have hornblende and plagioclase can be stable together, plagioclase diopside, plagioclase garnet. So all these hornblende and garnet, so all these tie lines have been drawn. Now, depending on the composition, let's say that the composition of the mafic rock, okay, lies in this region. So what would be the assemblage, mineral assemblage? Okay, from your ACF diagram, knowledge of your ACF, what would be the assemblage? Come on.
So it is the amphibolite phases.
All right. From this ACF diagram. So if we have drawn these tie lines and we have defined, okay, the bulk composition will be within this range. So what will be the composition, mineralogy or the minerals present in this rock?
So
So
plagioclase and
plagioclase,
hornblende.
hornblende.
Plagioclase and hornblende. Very good. So majority of the rocks, if it is in this region, would have only plagioclase and hornblende. Now, if it is within this region or this shaded this part, if it is with this region, means slightly more iron, magnesium, and aluminium rich, then what would be the assemblage?
So plagioclase, garnet and hornblende.
Plagioclase, garnet, and hornblende. Very good. And if it is slightly more calcium, aluminium poor, and calcium rich, in this
Then
region,
it will be plagioclase, dioxide and hornblende.
plagioclase, dioxide, and hornblende. See, now you can do it very nicely. So what you see is that in the amphibolite species, the different options are you have to have plagioclase and hornblende. Okay, depending on the composition, if the bulk composition is slightly aluminium rich, then we can have garnet. If the bulk composition is slightly calcium rich, we can have clinopyroxene. So we can have garnet, we can have clinopyroxene, plus quartz is already in the diagram. We can have some amount of quartz, and we have shown on what conditions epidote can be present. But whatever you do, if you have this diagram, stability diagram, SCF diagram, wherever is the composition within this shaded region, plagioclase and hornblende is the must. Okay. So typically two phases, hornblende and plagioclase, that's the characteristics of the amphibolite species. More important, the rock name is amphibolite. Okay, so the metamorphic rock of mafic bulk, which forms in the amphibolite facies, is called amphibolite. Okay, so I gave these questions in the test as well. Similarly, you need to understand what is the difference between the amphibolite facies and the rock amphibolite. When I say amphibolite facies, it's a range of pressure and temperature condition, and which is applicable to any rock type. But what is amphibolite? Amphibolite is a rock which is metamorphosed in the amphibolite facies only of the mafic bulk composition. Okay, as the names of the facies has come from the metamorphosed mafic rocks, right? The first to name the facies actually studied the metamorphosed mafic rocks. Therefore, the names of the facies actually came from the names of the rocks. Okay, or otherwise that the names of the rocks actually came from the name of the facies. So it was named as amphibolite facies. Now the mafic rock, which was formed within this fresh PT condition, has been called an amphibolite. So amphibolites are typically black rocks with up to 30% white plagioclase. Garnet is more in Al, Fe rich and calcium poor mafic rocks, as I said, within this region, and clinopyroxene Al poor calcium rich rocks in this region. Okay, so this is what is amphibolite. Let's skip this slide. Okay, so it may not be clear in the sharing the pictures, but when I send you, you can see it. So this is how a typical amphibolite looks like. Okay, we call it a salt and paper texture, where these black and white, it's practically black and white, where the black regions are all hornblende and the white regions are plagioclase. Okay, so the black regions are hornblende and the white regions are plagioclase. So it's a black rock with spotted white regions, which are the plagioclase. This is a typical look of an amphibolite. Okay, if it has a gneissic texture, okay, if it has a gneissic texture, then it is called an amphibolite gneiss. If it does not have a gneissic texture, it is just called an amphibolite. Okay, right. So the gneissic texture sometimes is not visible in the hand specimen. Maybe you have to look at the outcrop to see the foliation. But many a times the foliation cannot be seen, and then we call only an amphibolite. The picture out here is a garnet bearing amphibolite. If you can see the red dots, I don't know whether you can see it. Okay, but here is the red dots, which are actually the garnet, and this is a garnet bearing amphibolite gneiss. Okay, where the composition
Sir,
of this
but the
rock is
red dots
slightly
are
more.
maybe, yeah, sir, but
Sorry?
the red dots may be a plagioclase. Sir, it may be a plagioclase. Key feldspar.
No, no, no. The red dots. These red dots are garnet. Why do you say it as a plagioclase?
Sir, I mean K feldspar or orthoclase.
No, K-feldspar. Did we say any K-feldspar in the mafic rock? Is it potassium rich? So what have we studied so far? We are
No,
talking
sir,
about
I'm
only
just
plagioclase
looking just.
feldspar, right?
Yeah, no, just from the picture, it seems like
No, from the picture, even if
it.
from the picture it looks like, would you scientifically, after studying, say that this might be K-feldspar?
Oh no, sir.
Yeah, then why should you worried about K-feldspar? There should not be any K-feldspar. Mafic rock is a potassium poor, so we can't have so much K-feldspar in the rock.
Yeah, yes, sir.
Yeah, so it's not only by
Okay.
looking, you have to apply your theoretical knowledge as well before interpretation. Okay, so these are all the garnet dots, and this is a garnet bearing amphibolite gneiss, right?
Yes.
One important thing to note out here is that till the green schist facies, we have prevalence of chloride. Okay, chloride is a schistose mineral, and due to the prevalence of chloride, the rock was schist, or it has a well-developed foliation defined by chloride, and we were calling it as a schist. Okay, So green in color and schistose in texture, that's why it's called a green schist. Now, when you come to the amphibolite species, the chlorides are completely gone. Okay, so that's the boundary of the green schist to amphibolite. The chloride is completely gone, and we have only hornblende and plagioclase. None of them is a schistose mineral, and therefore, even if there is a deformation, okay, if these rocks are deformed, the manifestation of the deformation is not so prominent because there are no schistose minerals in this, and therefore, even if there is a deformed, we have a weak foliation, and therefore it is called a gneiss. Okay, there is no schistose mineral, and this rock is no longer a schist. Now, if you look at the thin section, okay, it would somehow look like this, where all these green ones are hornblende, okay, and these white minerals in plate polarized light, these are plagioclase. And if you look at this diagram, you can feel that there is elongation of this hornblende in a particular direction, which gives rise to a very weak foliation, and this is what is called as a gneissosity, and therefore we call it as a gneiss. But many of the hornblende amphibolite gneiss do not show such weak foliation, and then we call it only as amphibolite. For example, out here, if you look at the diagram out here, so it is very hard to find out a kind of a strong foliation, and therefore it's called an amphibolite. Okay, if it has an gneissosity, if you can see a foliation, then it's called amphibolite gneiss or only an amphibolite. What I wanted to show out here is that see, this might be maybe a slightly lower grade amphibolite where it is more greenish in color, the hornblende. And if you look at this rock, the hornblende has become more brownish. Okay, hornblende is strongly pleochroic. I'm not sure whether you have seen that in your mineralogy course. Have you seen that in your mineralogy?
Yes, sir.
Have you seen hornblende? You have seen hornblende in your mineralogy course.
Yes. Yes, sir.
Okay, so what you see out here is that this has become more brownish, and you can see different colors because these are pleochroic, and if you rotate it, single grains will also change its color. But what is it? From brownish to kind of brownish to kind of olive green in color. So that's the range. This is a typical olive green color. Okay, that is the range of color it shows. Okay. So this is the range of pleochroism, which is shown by hornblende. And what you see, these light greenish ones, okay, these light greenish minerals, these are all clinopyroxene. Okay, these are clinopyroxene. So this is a rock now, which has hornblende plagioclase as well as clinopyroxene, right? And here are some pictures as well. So you can see some polygonal texture out here where you see the straight grain boundaries between the different grains. So this all indicates that we have reached a substantial high temperature of metamorphism where the grains have recrystallized and formed polygonal nature, very similar to that many of the igneous textures. Okay, the rock has become much more drier. Okay, there's a lot of water is lost, but there is still enough water in the hornblende. But there is no other. Plagioclase is not a hydrous mineral, so there is no more. Whatever some water is there within the structure of hornblende. Okay, this is what is the amphibolite species is all about. Okay, now at the end of the amphibolite species, what happens is that a typical assemblage at the end of the amphibolite species is obviously hornblende plus plagioclase. Epidote is completely gone. Okay, epidote is completely gone, and we have either clinopyroxene or garnet and some amount of quartz. This is what remains at the end of the amphibolite species. But the dominant, always remember, hornblende and plagioclase is the most dominant mineral. Can be either clinopyroxene or garnet and some amount of quartz. Okay, so as you can see that very less amount of quartz, so it's nearly quartz free, and the rock is becoming more and more anhydrous. So the point is here we started with a very dry rock which got hydrated. That is the starting of metamorphism. Okay. All the minerals at the prehnite pumpelite, joycite, prehnite pumpelite, and then into the green schist species, majority of the minerals was hydrous minerals, and slowly the minerals reacted out, and the water is released, and the rock became drier and drier until we reach the amphibolite species, which is relatively dry. And now we will move into the granulite species and see that the rock will become completely dry. So we start with, let's go to the granulite phases and we'll see. Okay, so the changes occurring at the end of the amphibolite phases, when we move from amphibolite to granulite, the rock becomes relatively more anhydrous, relatively. Still, there is a lot of hornblende, which means that it has hydrous or it has water in its structure. Quartz is very less, nearly quartz free. Very important, epidote is completely lost. Okay, anorthite content of plagioclase becomes 50 to 60%. So as epidote is lost, all the calcium goes into the anorthite content of plagioclase. So in the green schist, the anorthite was only 3 to 5%. Okay, when you entered the amphibolite species around 500 degrees centigrade, it was around 15 to 18 to 20%, and then you reach around 700 degrees centigrade at the end of the amphibolite species. The anorthite content of plagioclase is nearly 50 to 60%. So there is a constant increase of the anorthite content of plagioclase. So it becomes more calcium and aluminium rich. Okay. Okay. Any questions so far before we move on to the granulite species conditions? Any questions so far?
No, sir.
Sir,
Okay.
in the
So
amphibolite phases,
yeah.
so how that water saturated granite solidus line is affecting it, or it has no direct relation
No,
with the amphibolite phases?
it has no direct relationship with that, this yellow line. It is just shown as a reference. Okay, so this just shown a reference. This becomes handy or important when we are talking about when we are will deal with pellitic rocks. Okay, because there the melting takes place, and this will become more relevant. But here in this case, this yellow line is not really relevant. It is shown out here, but not really relevant.
Okay, sir.
Okay. Okay, so let me ask again. Nitya, so what's the typical assemblage of the amphibolite species? How do we recognize an amphibolite? Yeah, Nitya, are you there? Okay, so she doesn't seem to be there. Okay, Subhash Thakur.
Yes, sir.
So how do you recognize an amphibolite species rock?
Sir, there will be most dominant minerals like MP balls and hornblende, like plagioclase and hornblende.
Plagioclase and hornblende. So what is the difference between? Okay, let me ask somebody else. Who is here? Nandan. Nandan, are you here?
Yes, sir.
So what is the main difference between amphibole in the green schist species and amphibole in the amphibolite species?
Sir, actually, I'm not following the lectures because I have not attended the previous some classes.
So you
So,
are why are you not following this lecture then?
sorry, sir, I could not tell right now. I'll go and recall and I'll respond in the next classes.
Yeah, so this is very easy to say this, but this is not at all correct. So as you are getting the video lectures, this doesn't mean you will not pay attention in the class.
No,
Okay,
sir.
you may have missed it. Yeah. So
Sir,
whatever I'm asking is from the class what I have taught today. Okay. So getting the video lecture is not an excuse of not attending or paying attention to the class. Okay, Sharmishta, what is the difference between the amphibole and the green sheath species and the amphibolite species?
Sir, there will be the pressure difference, like.
No, I said what is the difference between the amphibole? Amphibole is present both in the green sheath species and the amphibolite species. So how would we differentiate or identify? Okay, this is the amphibole which is formed in the green sheath species. This is the amphibole which is formed in the amphibolite species.
So in the green cyst faces, it come it as a
Sorry?
so in the green cyst faces, there will be there will be
No, we are
epidote.
talking about amphibole. See, you are also not paying attention. So all these things have repeated so many times in the last 40 minutes. And you have not been paying attention.
Like in amphibole, this epidote will be present.
We are talking about, so do you understand the question? I am talking about the mineral amphibole in the green sheath species and in the amphibolite species. What is the difference? So if you do not if you do not pay attention to the class, I must say that I would be very reluctant in sharing the video. I'll not be sharing the video unless I see that you pay attention, minimum attention in the class.
Sorry, sir.
Yeah. So that's Dr. Das. Nitya is not yet here, so she is just gone.
I'm here, sir.
So why didn't you reply at that time? Okay, that's Dr. Das.
Yes, sir.
So what is the difference? What is the difference between the amphibole in the green sheath species and amphibole in the amphibolite species? So that's Doctor. When you're asking, please use a microphone. Sorry, use a headphone. Otherwise, there's an echo.
Sir, I currently don't have a headphone with me, so I'm using the normal microphone of like that.
Okay, answer the question.
Sir, I guess difference in temperature. Okay,
tell me first the question. Explain me first the question, what I asked.
It was like difference of amphibole in green cyst species and amphibolite species.
No, difference in amphibole the green shift and amphibolite mean.
Okay, so hello, sir.
So if
Hello.
yeah, please go on.
Yes, sir. I think the difference in temperature.
So you did not even understand the question. That's why you are answering like this. So I won't be sharing the video lectures till I take the next class test. If this is the condition of the class, I won't be sharing the video lectures till the next class test. The idea of sharing the video lectures is to enhance, not, it should not be as an excuse that you don't pay attention to the class. Okay, this is becoming a disease and it cannot go on. Just log on and stay and you don't listen to anything, that cannot happen. Okay, I'm wasting my time. I'm giving my best so that you can understand, and many of you are just not interested in listening. Okay, if you are not listening, if you do not pay attention to the class, be bold and tell that I do not want to join. So Nitya, as you are back, please tell me the answer.
So are you asking chemical composition?
Sorry?
Can you repeat the question, sir? Like
No, you please.
you
I have
are
asked the
asking
question
different.
several times. Please repeat me the questions. I have forgot.
No, you were asking how will we recognize green shoots and amphibole?
No, that was not the question. Please recall the question and tell me. I've said it enough several times. So who can tell the yes?
Amphibole and green shoot faces.
So who can tell the question to Nitya? So she has
Sir,
not listened to the question at all, as she was not here. Who
yes,
can
sir.
tell the question to Nitya?
Yes, sir.
Question.
Yes, sir.
The question is, uh, how is the amphibole in the green cyst different from the amphibole in the uh, next one is amphibolite phases?
Yes. Okay. So Nitya, have you got the question? Please tell me the answer.
Actinolite and green shoot faces.
How is it different? That's what I want to know.
It is hornblende and amphibole fight faces.
Yeah, what's the difference between them? What's the difference between them? Quick. Yeah, if you know the answer, please tell. Otherwise,
I'm
do
not
not.
sure, sir.
Okay, why are you not sure? What is the problem? Where is the problem? Please tell me.
I was not paying attention to this class, or I went out for a minute. And
You went out for? You went out for? Sorry.
I went out because my mother called me and I did not hear.
Okay. So is it, do you think, is it right?
No, sir, sorry.
that I feel that everybody is listening, and then you are not even in front of your computer or phone or whatever it is.
Sorry,
See,
sir.
you need to understand, all of you, you need to understand that we are all spending time. We are trying as hard as possible. Okay. I would have liked to, for everybody to switch on the camera, but it's always that all of you complain that it's a data driven thing. We are using a lot of data and so on. But I would always prefer that you, when you attend the class, you stay in front of the computer, then at least you try to be a little bit more attentive. If you do not try, I'm here regularly on the class times, wasting my time, putting my entire effort to make you people understand. And if you are being so careless about just logging in and taking advantage of not switching on the camera and just going away, does that make sense? Does that make sense, Nitya?
Sorry, sir.
And this is for all. And the result is that I'll be very reluctant to share the video lectures, and the sufferers would be the ones, those who are trying to attend the class and paying attention. The problem is the video lectures. As I'm sharing it, you feel that you can see it on your own sweet time, and there is no need of paying attention during the class time. It's just a mockery that you just sign in and then you are gone. Obviously, I don't have the time every day to call each one of you to find out whether you are attending or not, and you are taking the advantage of it. In fact, many just don't attend the class. I would say they're at least better off in the sense that they have the courage to do that, rather than attending and not paying attention. This goes to all of you, those who could not answer the question or even understand the question. Alok Kumar Sahu, tell me.
Is higher in amphibole physics. Yes, sir. The question is how is amphibolite phases is different from amphibole of green cyst phases.
Okay, very good. Okay, and what's the answer?
Yes, sir. The aluminum content is higher in amphibolite phases than the green cyst phases.
And what is the name of the common amphibole in the green cyst species and the amphibolite species that we find? The most common amphibole of the green cyst species and the most common amphibole of the amphibolite species.
Yes, sir. Actinolite in green cyst.
Yes, very good.
And in hornblende in amphibolite.
Hornblende in amphibolite, very good. Okay. Okay, so let's move on. But this is not something. Please keep this in mind. This is not something which is doing you any good. Okay. If you continue to do like this, and I get the impression that you are not paying attention to the class, just attending and not there. Okay, I'll modify my ways, right? And you might not like those. Okay. For example, right now I've decided that one of the class tests, one of the components, I'll keep a Viva, one-to-one Viva, where in place of it. I'll spend a lot more time, but I'll do that in a one-to-one Viva for all as a part of the internal assessment. Okay. So what we move on now is the granulate facies condition. And what is granulate facies? The temperatures above 700 degrees centigrade. Okay. So when we move on to the granulate facies, the typical mineral assemblage is along with typical mineral assemblages, orthopyroxene, clinopyroxene, and plagioclase. Right. What you see out here, there are certain things to note. What you see out here is that it is typically a anhydrous mineral assemblage, right? Hornblende is gone. We'll come to the reactions, obviously, but hornblende is gone. Okay, hornblende is gone completely by this reaction. Okay, so hornblende plus quartz actually forms orthopyroxene plus clinopyroxene plus plagioclase plus water. Clinopyroxene, as you have seen, that can be present in the amphibolite facies as well. Okay, I've showed you the pictures. Along with hornblende, and clinopyroxene can be present, but orthopyroxene entry or formation of the orthopyroxene marks the entry into the granulate facies condition. So whenever we find orthopyroxene in a mafic rock, only then we can say that it has moved into the granulate facies condition, which is more than 700 degrees centigrade. Okay, so what is the reaction takes place? So there is a hornblende breakdown reaction where hornblende reacts with the available quartz to form orthopyroxene plus clinopyroxene plus plagioclase plus water. Okay, so as you can see that the calcium content of the hornblende breaks down to form orthopyroxene. Orthopyroxene does not have calcium or aluminium. Okay, so the calcium and aluminium component of the hornblende goes into clinopyroxene and plagioclase. Okay, so we have orthopyroxene, clinopyroxene, and plagioclase with the breakdown of quartz. Another important thing to note out here is release of water. Okay, so the rock becomes more and more anhydrous. And the typical mineral assemblage, what we see is orthopyroxene plus clinopyroxene plus plagioclase. And this mineral assemblage is a typical anhydrous mineral. There is no mineral anymore which contains water. Okay, this rock is called a mafic granulite. Okay, so it's a mafic bulk composition, and within the granulate facies, the name of this rock is a mafic granulite. Many times it's also called a 2-pyroxene granulite because both the pyroxenes are present together. It is only in the granulite facies condition that both the pyroxenes, orthopyroxene and clinopyroxene, in a metamorphic rock is present together, and therefore it is called a 2-pyroxene granulite. Very commonly, we will see we'll come across this name as well as mafic granulite. These are the names which are given to this rock. Very important, this sentence, appearance of orthopyroxene marks the entry into the granulate facies. Just a moment. Appearance of orthopyroxene marks the entry into the granulate facies condition. Okay. Yeah.
Sir, for example, in the green cyst, also the rock green cyst is formed from mafic minerals, and those for the amphibolite, that also from mafic. So, what is the reason of writing here mafic granulate?
Sorry, can you just repeat the question once?
Sir, sir, you told that when we tell green cyst, then that is a mafic that is a मतलब मैफिक रॉक होता है, मतलब जो क्या कहते हैं ग्रीन सिस्ट रॉक है, और वो मैफिक मिनरल असेंबलेज से बना है, और वो ग्रीन सिस्ट कंडीशंस में बना है, और सेम अप्लाई करते हैं कि एम्फीबोलाइट में भी वो मैफिक से बना है. तो यहाँ पर हम लोग ग्रेनुलाइट में भी मैफिक वर्ड क्यों यूज कर रहे हैं, मतलब हर जगह.
Okay, so I understood. Yeah, I have understood. See, well, then you can call it as a 2-pyroxene granulate. Why it is mafic? See, these are all These are all names which have come for a long time, right? Why is it so? Because granulite. Okay, so any rocks which are formed in the granulite species condition, whether it is a mafic bulk or a different bulk, they have a different character altogether. Because it's so high temperature metamorphism, they have a different character altogether. Okay, normally when you say a granulite, okay, it is a very commonly used term. So there is no specific formula how you use it, but it's a very commonly used term that the granulites, many a times we refer granulite to other bulk as well, which has metamorphosed in the granulite species condition. Okay. Therefore, to distinguish this one from the other, we sometimes call it as a mafic granulite. You are absolutely right that we can call it only as a granulite, and there is no point in saying mafic, because by granulite we should actually mean that it has come from the mafic rock. Okay, but this term granulite, unfortunately, is used commonly for other granulite species metamorphosed rocks as well. Okay, that's why it's very commonly we say it as a mafic granulite. It's a commonly used term. You can call it as a 2-pyroxene granulite as well. Okay, 2-pyroxene granulite is unique because no other bulk composition will produce both the pyroxenes together in a granulite species condition. If you have both orthopyroxene and clinopyroxene together, this is only mafic rocks that can produce this. Okay, in a metamorphic rock.
Yes.
Okay. Okay. Now,
So,
if
sir,
you look at
so,
this,
sir,
yeah.
so सर बेसिकली ग्रेनुलाइट में अदर बल्क कंपोजिशन से भी ग्रेनुलाइट बनता है, ना कि सिर्फ मैफिक से.
Granulite तो बनता है. Definitely, it goes into the granulite species. Okay, and many a times, commonly, although it is not technically correct, but commonly we call them as granulite as well. Okay, we use a prefix to it, but we denote them as granulite.
Okay, sir. Thank you, sir.
Okay, if you say it mafic granulite, then it is absolutely clear that it is a mafic rock, mafic bulk composition, and metamorphosed in granulite species condition. Okay, so
Okay,
what
sir.
we have done in this ACF diagram, yeah, just a moment. So what we have done in this ACF diagram is that we have joined all the mineral assemblages which are which can coexist together. We have clinopyroxene, we have plagioclase, we have garnet, we have opiate. Okay. Now what you see is that depending on the bulk composition, you can have slightly different compositions. Now majority of the bulk lies in here. Okay, so if you have anything in this region, so what you have is OPX, CPX, which is augite, orthopyroxene, and plagioclase, which are stable. Okay, if you have a slightly higher aluminium-rich bulk, then along with OPX and plagioclase, rather than having clinopyroxene, you can have garnet as well. Okay, at medium pressure conditions. So this is what is this diagram is made for the medium pressure condition. Okay, we can have garnet as well. Now at high pressures, what happens is that orthopyroxene plus plagioclase, there is a reaction relationship where orthopyroxene and plagioclase gives rise to garnet and clinopyroxene. So now if you join this line out here, garnet and clinopyroxene, so what happens is that then this line would be gone, cross-cutting tie lines. Then what we'll have, OPX plus plagioclase can react to form clinopyroxene and garnet. Okay, so now if you are on the right side of the reaction, where OPX and plagioclase is completely gone, then this line, this black line is not there. Then we have a triangle like this. Okay, So you see, majority of the bulk composition out here lies within CPX, plagioclase, and garnet. Okay, and if you have compositions in here, you have plagioclase is completely gone, where you have garnet plus, if it is more FeMG rich, calcium aluminum poor, a restricted bulk composition, then we have CPX, garnet, and orthoperoxide. Okay, so basically at high pressure assemblage, very commonly what we have is clinopyroxene plus garnet plus plagioclase plus quartz, obviously, plus minus orthopyroxene. Okay, so orthopyroxene in granulite phase conditions in medium pressure. As we increase the pressure, this tie line of plagioclase orthopyroxene replaced by a tie line of garnet and CPX, where orthopyroxene and more consumed, and what we are left with is clinopyroxene, garnet, plagioclase, and quartz. Agreed? Understood?
Yes, sir.
Sir, here you was talking about is the ACF diagram is under a medium pressure temperature, but if I'm not wrong, so but here we are talking about the high pressure, high temperature
Right.
conditions. So why it is so,
High
sir,
pressure? No,
different?
this is sorry. Go on.
I mean the high temperature here in the granulate phases we are looking for the high temperature phases, but in the diagram you mentioned that it is a medium pressure diagram.
No, what I mean
medium.
is that where is the facies diagram? Yeah. So within the granulite facies, you can have, so the pressure range is huge for granulite. You can see. So you can have this pressure as well as pretty low pressures, right? So it's a huge pressure range. Now, if I divide this, so at low pressure condition and high pressure condition. Okay, within the granulite facies means above 700 degrees centigrade. See, granulite facies is defined by above 700 degrees centigrade. There is no mention about the pressure. Okay, the pressure has quite a lot of variability till around let's say 1.4 GPa, which is around 14 kilobar. You can still be in the granulite facies. Okay, so there is but in the lower pressure condition, relatively lower pressure, orthopyroxene is more prevalent. If we go to the relatively higher pressure, then the orthopyroxene is no longer stable. It starts reacting with plagioclase to form garnet and clinopyroxene. That is what I tried to show you with this diagram, that if you go to relatively higher pressure, then this tie line connecting plagioclase and orthopyroxene, the tie line connecting plagioclase and orthopyroxene is gone and is replaced by the tie line connecting garnet and clinopyroxene. Obviously, cross-cutting tie lines cannot exist. If the tie line is cross-cutting, which means there is a reaction relationship between them, and that is what we see, orthopyroxene and plagioclase forming garnet plus clinopyroxene. Now, if you are in the higher pressure side, when this triangle is present, plagioclase, clinopyroxene, and garnet, then the majority of the bulk composition of the mafic rock will form clinopyroxene, plagioclase, and garnet. Some restricted composition will not have plagioclase, okay, which is aluminum and calcium poor, will have garnet, clinopyroxene, and orthopyroxene. Okay, but majority of the mafic rocks at slightly higher pressure conditions within the granulite facies will have garnet, plagioclase, and clinopyroxene, plus minus orthopyroxene. In nature, what we see is that all these reactions doesn't go to completion. It means that all the orthopyroxene may not be completely consumed. So in a rock, what we will find is that some orthopyroxene is still left, right? Along with that, we have garnet, clinopyroxene, and plagioclase along with orthopyroxene. So many times we find all the four minerals together: garnet, orthopyroxene, clinopyroxene, and plagioclase. Okay, and as I said as well, that these minerals, as they are more solid solution minerals, the reactions don't take place at a particular pressure temperature. These are all sliding reactions, which means takes over a range of pressure and temperature conditions. Okay, so many a times in the natural rock, we find all the four minerals together: garnet, orthopyroxene, clinopyroxene, and plagioclase.
Sir, can you go to the phases diagram, please? Yes, sir. Sir, in the lower region of the granulite, lower pressure region. So why is that water saturated while?
No. This is the water saturated granite solidus is this yellow line. Okay. As somebody asked, I think Aditya asked, I told that it is marked out here in this diagram, but for mafic granulites, this is not relevant.
Okay.
Okay, you don't have to worry about that. Just forget about it. Okay, this yellow line becomes relevant when we are talking about the pellitic rocks. Now just forget about that. I can't, these diagrams already, I can't create a diagram just taking out the yellow line. Okay, it's much, so I kept it. But in this, for the mafic granulite, it's not really relevant.
Okay, sir. And sir, which tile line will be remain present
in this ACF diagram?
Okay, I think one by one. Sai Raman Patra, go ahead.
Yes, sir. I am asking that which tile line will remain present and the new one will be formed. That is depend on the stability or something else.
Once again, I did not get your question.
So initially the tile line is connecting plagioclase and orthopyroxene. Then the next tile line at high pressure it is connecting augite and garnet.
Right.
So is it depend on the stability of the minerals or
yeah, it depends on the stability of the minerals. So at higher pressure, that's why that higher pressures we have to draw the diagram differently, because that as we increase the pressure, orthopyroxene reacts with plagioclase to form garnet and clinopyroxene. Okay. And this reaction is a pressure dependent reaction, which means in a PT slope, if we have temperature on this slide and pressure on this slide, it will have a shallow slope, which means orthopyroxene plus plagioclase will be on the lower side, lower pressure side, and garnet plus CPX on the higher pressure side. Again, why is it so? As I said, garnet is a much more dense mineral and it is always favored at a higher pressure condition. So within the granulite species, if we move to higher pressures, then OPX plus plagioclase becomes more unstable, garnet and CPX becomes more stable. Okay, and then this tie line will be replaced by the garnet CPX tie line.
Yes.
Okay. Okay, so this is the typical, the network seems to be a little bit not so good. So this is a typical look. When I share the slides, you can see at it. There's a typical look of a granulite species mafic granulite. Okay, one thing I missed to say. Okay, this composition, tell me, from which rock it has a similarity? This mineralogical composition, OPX, CPX, plagioclase, what rock can you think of which has the similar mineral assemblage? Quickly, what rock can you think of which has a similar mineral assemblage?
Sir, gabbronorite.
Gabbronorite, right? So it's an igneous rock, mafic igneous rock. So what you see is that, so as OPX, CPX, and plagioclase, so what you see is that you started with a mafic rock, which probably had the same mineral assemblage except the olivine, dominated by pyroxenes and plagioclase. Okay, so you started with a hydration of these minerals to form hydrous minerals, and then you started increasing increasing the pressure and the temperature.
Sir, your
the
voice
rocks become more and
gone, sir. Sir, your voice was gone, sir. Can you repeat, sir?
No, I did not say anything. I actually stopped.
Okay, sir.
Okay. So yes, so we started with orthopyroxene, clinopyroxene, and plagioclase, right? This was the anhydrous mafic igneous rocks with the same anhydrous mineralogy or similar anhydrous mineralogy. You started with hydration, forming hydrous minerals, started increasing the pressure and temperature. As we moved on, the rocks became more and more anhydrous. Now you reach the granulite facies and you have the same exact mineralogy. But what will be different? The texture, the look of it will be completely different. Obviously, along with garnet, garnet is not there in the, never there in the igneous rock. Okay. But otherwise, except the garnet, this mineralogy is very same or exactly same as that of the mafic igneous rock that we started with. Okay, that's a very interesting part of the metamorphism of the mafic rock, that what we start with the hydration, ultimately after metamorphism, we reach such a condition. Okay, this is a typical look where the red ones are all garnet, white ones are plagioclase, and the black ones are pyroxene. Okay, a typical granulite facies rock or a mafic granulite with garnet. And if you look under, the internet is slightly slow, it's not changing. So if you look at under the thin section, this is how it looks like. Okay, it's a mafic granulite or a 2-pyroxene granulite. I'll show you in the practical. These brown ones are the orthopyroxene. These brown minerals are orthopyroxene. No, yes, I think these brown minerals are orthopyroxene. These green ones are clinopyroxene, and these ones and the colorless ones are all plagioclase. Okay, this is how it looks like under the microscope. More closely, these are the orthopyroxenes, these are plagioclase, and these are clinopyroxene, the green ones. Okay, so I write it down: plagioclase, OPX, PPX. That's it. Okay, and if it is garnet bearing, you can find such large or some garnets within the same assemblage as well. Okay, garnet along with OPX, PPX of plagioclase. Okay, so if you look at this diagram,
So can you
now,
go back one slide, please? So there is garnet written on the. Is that garnet written the right side top corner?
yeah, but that's a mistake. Sorry, I think this should go. Sorry, that's a mistake. I did not notice it. So this is wrong. Maybe this one looks like garnet. Maybe it has moved.
Okay.
Okay. Yeah, that's wrong. Sorry, you pointed out correctly. So the green one cannot be garnet. I think while marking on the slide, I wanted to mark this. The writing moved towards the left. Okay. So what you see in the granulite facies, very important. So look at orthopyroxene. Okay. So it starts at the granulite facies, which means that this is not found in the amphibolite facies. The appearance of orthopyroxene marks the entry of the granulite facies, and it more or less continues throughout the granulite facies condition. Okay, it's very important. This is the orthopyroxene as the characteristic mineral of the granulite facies condition. Garnet, as you can see, it's dotted in the amphibolite facies, which means that for certain conditions, certain PT conditions and certain compositional conditions, garnet can be present in amphibolite facies conditions, but it is prevalent in the granulite facies. But it is only orthopyroxene which can which is only starts from the granulite facies condition. Look at hornblende. Hornblende starts, can be there some variations of hornblende, but dominantly hornblende starts from the amphibolite facies. It is all throughout amphibolite. It is the characteristic mineral. It can spill over into the granulite, some restricted composition, but very less. Okay, but a little bit into the granulite facies, it is no longer there. Amphibolite is gone. Look at clinopyroxene. Clinopyroxene occurs at the very high end of the amphibolite facies, can occur at certain conditions, but it is very prevalent in the granulite facies condition. Plagioclase is obviously present, but changes its composition. So in the granulite, the main minerals are plagioclase. Okay. This is clinopyroxene, orthopyroxene, garnet. Okay. This is what the granulite pitch is made of. On the other hand, amphibolite is mainly plagioclase and hornblende. Okay, plagioclase and hornblende. This is again the schematic diagram from the green schist amphibolite to granulite. You can see out here that the hornblende moves and breaks down into orthopyroxene and clinopyroxene. The plagioclase changes its composition. Okay, and these are the mineral assemblage which is in the granulite species composition. Olivine is very rare and can be found in also in metamorphic rocks at very high temperature, but it is very rare. Okay, very rare. Dominant mineral assemblage is orthopyroxene, clinopyroxene, and plagioclase. Okay, any questions so far? Okay, if not, I'll just take a 2-minute break to get some water and come back in 2 minutes. We have today we have taken the break in asking questions, and I can't afford to give you a longer break. We need to finish a little bit, cover something more, the blue schist and the eclogite. So I'll leave you a little bit before 11. For that, we will continue so that you get a little bit break after this class before the next class. Okay. So 10-15 minutes before 11, I'll leave you. Is that okay?
Okay, sir.
Yeah. Okay. So what we are left with, if you look at the PT diagram, so we have covered along this medium PT series we have moved to the zeolite, perenite, pumpelite, green schist, amphibolite, and veronite facies. Okay. So what we are left with, just to understand the characteristics of the blue schist and the eclogite facies, which is within the high P by T series and normally found in the subduction zones, which we discussed earlier. Okay. So we'll briefly look at that what are the characteristics of the blue schist and the eclogite facies condition. Okay. So as I said, majority of the metamorphic rocks are within this medium pressure by temperature, but obviously blue schist and eclogites also are very relevant metamorphic rocks in terms of understanding the global tectonics. Okay. So if you look at the blue schist facies along a high P by T series, depending on the geothermal gradient, you can enter from the perenite pumpelite facies, or you can enter from the green schist facies as well. Now, depending on the geothermal gradient. Okay. For example, if you can move here, or you can move through here as well. Okay. So depending on that, the reactions would be slightly different. Okay, because the mineral assemblage within the perenite pumpelite and in the green schist facies is slightly different. Therefore, the reactions will be different, but the mineral assemblage will be more or less pretty similar. Okay. One important thing what you note here is that the blue schist facies has a pretty wide, at least, yeah, some wide temperature range. Okay. Within the range of, let's say, roughly less than 300 degrees centigrade to around 500, 550 degrees centigrade. That's the range of temperature. But the main characteristic is that it is pretty high in pressure, or the pressure is pretty high. Okay, that's the, in terms of the PT space, that is where the blue schist facies lie. Okay, so the typical assemblage is a mineral called a glaucophane, which I showed you, already told you, which is an amphibole. Okay, so the main assemblage is amphibole, which is glaucophane. There is a mineral called lawsonite, epidote, quartz, chlorite, garnet. So these can be there. So the main primary assemblage is glaucophane, lawsonite, and epidote and quartz. These are the main minerals which are present in the rocks of the blue schist. So what you see is that again it is amphibole. Okay, but a different variety of amphibole. Now, if you look at this reaction, you don't have to really remember it, but the essence of it is that you have perenite, pumpelite, albite. Okay, this all combines to form mineral glaucophane and lawsonite, which are the formulas are given out here, which are glaucophane is the sodium, magnesium, aluminum bearing amphibole, and lawsonite is the calcium, aluminum, silicate bearing rock. What is important to note out here in glaucophane, as we discussed, that the sodium, these two sodium goes into the +6, means in the octahedral site. Okay, this sodium goes into the octahedral site out here in the glaucophane, replacing calcium. Therefore, a typical glaucophane is sodium rich and does not have any calcium, which is in stark difference with that of hornblende or actinolite. Okay, and this glaucophane is blue in color and it imparts the characteristic blue color in the rock. Okay, this is due to the high sodium content. As because of this high sodium content, this mineral is become blue and it imparts the characteristic blue color to the rock. It is schistose in nature due to the presence of amphibole, okay, glaucophane, and lawsonite. Okay, it is schistose in nature and therefore it is called a blue schist. It is schistose in nature, blue in color, and therefore it is called a blue schist rock. Okay, so again, the name of the facies and the name of the rock is the same. The rock is called a blue schist, and the name of the facies is also called a blue schist. Actually, the name of the facies came from the name of the rock. Okay, so the blue schist and the facies name came from the name of the rock, blue schist. Again, blue schist and blue schist facies is different. Blue schist facies refers to a PT, a range of pressure temperature condition. This pressure temperature condition can come in any bulk composition, okay? But if it is a mafic bulk, then the rock which forms is also called a blue schist. Okay. Now, so the typical mineral assemblage, as I said, is glaucophane, lawsonite, and epidote. Now, if you move from green schist to blue schist conditions, okay, as I showed out here, now if you move from green schist to blue schist, the similar things happen. Now, actinolite is the most common mineral in the green schist species. This is also an amphibole, but this is calcium bearing, aluminium poor, and sodium poor. Okay, calcium and FeMg bearing, and you have albite, which is sodium aluminium bearing. You have chlorite, which is FeMgAl bearing. So all these together, along with quartz, form actually glaucophane, which is a sodium aluminium rich amphibole, and lawsonite, which is a calcium aluminium bearing silicate. Okay, so this is the main mineral assemblage, glaucophane and lawsonite plus epidote in the blue schist species condition. Okay, so if you what is the difference between the green schist and the blue schist? The main difference: green schist is the presence of actinolite. It is also an amphibole, but it is sodium poor and aluminium poor. And blue schist species is an amphibole, which is called glaucophane, which is sodium rich and aluminium rich. Okay, sodium gets into the tetrahedral site, octahedral site of the amphibole only under higher pressure, and there it forms glaucophane. Higher pressures is without relatively higher, lesser temperatures, and that is achievable when we move into the blue schist species condition. So with increasing temperature in the blue schist, garnet becomes more stable. So now blue schist, as I said, has a range of temperature. Now when you are relatively at a higher temperature side of the blue schist species, then garnet becomes more stable, albite becomes unstable, and jadeite becomes more stable. Now what is the reaction? This is albite out here. If you take out a quartz from this molecule, what we form is a pyroxene. How it is pyroxene? Si2O6, that's the pyroxene formula. So rather than having Fe and Mg, we have sodium and aluminium by the glaucophenic substitution, and therefore this is called a jadeite. Not really by the glaucophenic substitution, this is called a jadeitic substitution, where Fe and Mg, 2 plus 2 minerals, let's say Mg plus 2, this is 2, gives 2 Al3 plus Na plus 1. So 2 into 2, 4, the charge is balanced, and you get aluminium and sodium in the octahedral site where Mg was there into the pyroxene. Okay, so basically the albite structure breaks down to form a pyroxene, which is sodium and aluminium rich, and quartz. So this happens only at very high pressure, and we can only see this in the blue schist species condition. Okay, so these are the characteristics. Very important to remember why it is called blue schist. The characteristic mineral is glaucophane, lawsonite, epidote. The blue color is imparted by glaucophane. Why does the blue color come? Presence of sodium in the octahedral site. Okay, this is how it looks like, the blue schist, really blue in color. If you would have come to the lab, means physically present, I have a small piece of blue schist. This is a common rock which is not found in India. Means in India we do not have such a condition where we find blue schist. Okay, but it is really nice and blue in color. Okay, this is due to the prevalence of the mineral glaucophane. These are the lawsonites, which are slightly grayish or light blue in color, but the matrix is all dominated by the amphibole glaucophane, and these rocks have very nice blue color. Okay, under the thin section, a microscope in the thin section, it also occurs as gives the nice bluish tinge due to the presence of glaucophane, and this variety of glaucophane is also kind of elongated, and you see it gives a nice foliation, a cystostructure, and therefore it is called a blue schist, a schist which is blue in color. Okay, any question? Any question with blue schist?
Sir, if there is a metamorphic transformation from a green cyst to blue cyst, then why not it is from amphibolite to blue cyst?
For that, you have to check the from
Here.
amphibolite. How can you go to blue schist?
Sir, because
we are
in
always
the
increasing with the geothermal gradient. The pressure and the temperature is increasing. Right?
Sir, but in the
so
retro,
if you increase from here, then we'll go into the eclogite.
Yeah, sir, but in the nature, the retrograde force,
Yeah, but the
retrograde is also.
retrograde reaction with increasing pressure, you won't find a natural situation where we can have a retrograde decreasing temperature with increasing pressure.
Okay, sir.
Yeah, just a moment. Yeah, so we do not have a natural condition where the PT conditions decrease. The pressure decreases. Pressure increases with decrease in temperature.
Okay, sir.
Okay, if there is a retrogression from amphibolite, it will go to green schist, not to blue schist.
Yeah, okay, sir, got it. Thank you.
Okay. Okay, any other questions? Okay, so there's the last thing what I'll do very quickly is give you an idea about what is paired metamorphic belts. Okay, and we will stop. So I give you the background is that in Japan, okay, where it was first identified, what people saw is that there is a narrow belt of rock which is blue in color, practically the blue schist, and behind that there is a narrow belt of rock parallel to it, which is green in color in here, which is actually amphibolite facies in condition. Okay. Now the question was that how can, in what kind of situation can you find two metamorphic rocks of contrasting pressure temperature conditions side by side, and what does it indicate? Okay, so a narrow belt of this rock, which is the blue schist rock, and the narrow green one is the green schist rock. Okay, it was first noted by a scientist Miyashiro in 1951 in Japan, and later it was found that it is a very interesting phenomena and gives a very important information. Now, to understand this, what we have to understand is the subduction scenario and what kind of metamorphism occurs at different places. Okay, let me go to this diagram which we already did. Okay, or we can do it out here as well. So this is basically your subducting oceanic slab, which is consisting of basalt or basaltic rock, the basaltic oceanic crust, and this is your island arc on the overriding plate. Okay, sorry, there's the island arc on the overriding plate. So what you see is that if you go to the next slide, you remember we did this diagram. Okay, you remember this diagram?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So what you see is that when you, if the mafic rock, the mafic oceanic crust, when it goes deeper into pressure, okay, deeper below the other one, the pressure increases instantaneously, but the temperature doesn't increase so much, and we see a high P by T condition, geothermal gradient, which is ideal for forming this blue schist rock, which is number 3. Okay. On the other side, on the overriding plate, okay, so the parallel to the blue schist, what we normally see is the number 5, which is the green schist rock, according to the geothermal gradient out here. Now, if this blue schist rock, okay, if this blue schist rock, due to mainly due to thrust faults, okay, mainly due to thrust faults, sorry, yeah, come up, right? Come up to the surface, right? And on the side we have, let's say, green schist. Now, if you explore this region now, if you explore this region, what will you find? So you will find first a region which is a blue schist rock, and adjoining you will find, just after that you will find a region which is of the green schist or amphibolite species. The main difference is that you find a rock, blue schist, which is high P by T, followed by a rock which is medium P by T, or in fact low P by T in many times. So high P by T rock adjacent to medium or low P by T rock, if we find such in a narrow belt like this, is called a paired metamorphic belt. Now, obviously, where do we find it? We can find it only where blue schist and these rocks can occur together or side by side, and this happens only in our subduction zone scenario, as we see out here. So what we see when we understand this, that these paired rocks or these rocks of the contrasting PT conditions can occur together only in a subduction zone scenario. When we find these rocks on the surface, okay, we call this paired metamorphic belts. And even if we do not see the subduction happening, okay, we can infer that there is a subduction zone scenario either presently or was there previously in the geologic past. Okay, let's just have a look at this, what is written, and then we can discuss on this again the next day. Okay, so what are paired metamorphic belts? These are elongate parallel belts with significantly different metamorphic rocks. Okay, belts with high pressure, low temperature metamorphic rocks on the oceanic side, associated with medium pressure, high temperature metamorphism on the continental side. To look at it, it is always the blue schist species rock, which is high pressure, low temperature towards the ocean. So this is the ocean, towards the oceanic side, and towards the land, which is the arc, we have, sorry, there's quite a lot of lag. This is the ocean. We have the rock which is medium pressure by high temperature metamorphism. Okay, so the high pressure, low temperature rocks were actually subducted. So these rocks, the blue schist species rocks, were actually subducted. The medium pressure, high temperature rocks are found above the volcanic or the continental arc. So these rocks are actually the subducted rocks. After subduction, it has come up to the surface due to tectonic processes. These are the rocks which are formed above the volcanic arc. Okay, it's most prominent in Japan because Japan is also an island arc, example of an ongoing subduction process, where it is recognized in many places throughout the world in ancient rocks, which was associated with convergent plate margins. Okay, therefore, this paired metamorphic belts are used for the identification of ancient subduction zones and plate boundaries. Also indicates the polarity of subduction. So if you don't see this part, if you do not have any idea of this part and you see only the surface, for example, the map of Japan, from the surface, and you map these paired metamorphic belts, you have an idea that what is the direction of the subduction going on. So if you look at this, then you can see this is the ocean. This way is the land, which means that the subduction is taking place from the ocean towards the land. If you look at the tectonic plates, you'll see that this is the Pacific plate out here, Pacific Ocean. This is the Pacific plate, which is getting subducted below the other plate and forming the arc, which is actually Japan. And we do see this paired metamorphic belt. So we have got this here, the active subduction is taking place. Okay, we know that there is a subduct, but many places in the ancient rock record, we no longer see the subduction, but we see the paired metamorphic belt, which indicates that it was a plate boundary or a convergent plate boundary at one point of time in the geologic past. Okay, I stop at this today. If you have any questions, please ask.
Sir, can you
Yes.
go back one slide? One more, sir. Yes, sir. Sir, the blue cyst that we are getting is in the middle of the continent, sir, not on the continental margin, sir, where the subduction is happening.
Yes, this entire thing is the arc, obviously, yes. Not really at the margin, but at the nearly at the margin, right? This is why it is preserved now, right? But what happens is that this is a completely a structure, means it is happening over a long period of time, and this is why it is now exposed. Maybe in this region, if you go deeper into the deeper from the surface, it might be exposed as well. Maybe these are now covered with sediments. That's why we do not see. This is the part which is now exposed, these rocks.
Okay, sir.
Okay. So okay, here it is not marked, which means that below we don't see blue schist. It not might be the case. It is that in this regions, okay, in this regions, what happens? There's a lot of sediment depositions as well. Therefore, we do not see, means these rocks are not exposed. Maybe deeper into the earth, we find this, but this is the part, this is the actual map, okay,
yes,
where it is actually exposed.
Yes,
and this is the place where we see this rock exposed on the surface.
Yes, sir. So we are not digging to get the blue cyst and
no. These are exposed now on the surface.
Okay, sir. Okay, sir.
Okay. There is a component of this coming to the near the surface, and there is also erosion to expose these parts on the surface.
Yes, sir.
Okay.
Yes, sir. It's okay, sir.
Hello, sir.
Yeah.
How they depict Barrovian zone here in the picture?
Where do you see? So basically, what is in the picture? What is said is that in this, it is the blue schist, and in this region, what you see, if you see all the facies, right? Okay. So Barrovian zone, maybe it's not the right term. I've taken the picture, so I did not have the control of the picture. What it meant is that the Barrovian metamorphism means that it is a medium. The Barrovian metamorphism occurs along a medium PT condition, right? Along the PT. Where is the PT diagram? So Barrovian metamorphism, in some ways, it means that along the medium P by T series. Okay.
Yes, under normal
and,
PT condition.
Yeah, and right.
In the
And
picture,
here,
it looks like some magma flow or something.
Right. Here it is magma flow in the arc, but the facies what you get from a prehnite pumpelite to green schist to amphibolite to granulite, this is what you find in the Barrovian zone as well. That's why it is sometimes called Barrovian. But if I would have drawn the diagram, I would have not marked in this way. Okay, I would write, so you forget about this Barrovian, I would write medium P by T. Okay, and in place of blue schist, here is high P by T. Okay.
Okay, and in the last, on the bottom
here
side
also I would not really write. Okay, this is a more suitable diagram I got, that's why I put it, but I did not edit it so much. Okay.
Okay, sir.
Yeah. Right. And then okay, anything else?
Sir, actually, I collected a sample, and that looks similar. The one you have shown with the plagioclase and the hornblende together. The
Where did you
black.
collect from?
Sir, I collected it from Jharkhand Koderma. Sir, mines nearby me.
Okay. So those are igneous rocks. Yeah, maybe.
Sir,
Yeah,
I
but
can
maybe
present
as
it.
well. Yeah, you can, when you come back to the institute, you can bring it along with you. I would love to see it.
Sir, I can present it. I
One,
made photos and videos.
yes. So maybe the next day. Today I'll also have to. You need a leave as well. Maybe the next day
Yes.
would be interesting. You can present the photo or show me the sample by switching on your camera. We can discuss definitely.
Okay, sir.
Okay. Remind me the next day, next theory class. We can surely see it.
Okay, sir.
Okay.
Yes, sir.
Yeah.
Sir, actually, I tried to search around, and people told that that is moonstone, and